When dealing with equipment grounding conductors, or EGCs, in PVC conduit containing multiple circuits, specifically 20 amp circuits where conductor sizes have been increased to mitigate voltage drop, sizing the EGC requires careful consideration of the National Electrical Code (NEC). The primary sections to consult are 250.122b and 250.122c. Let's dissect these sections and illustrate how they apply. NEC Section 250.122b addresses situations where circuit conductors are increased in size. The code states the equipment grounding conductor must be increased proportionally according to the increase in circular mil area of the ungrounded conductors. This provision primarily deals with scenarios where voltage drop necessitates upsizing the circuit conductors, and consequently, the EGC must also be upsized to maintain adequate grounding impedance. Now, NEC Section 250.122c provides guidance when multiple circuits are present in a single raceway or cable. This section stipulates that the equipment grounding conductor can be sized based on the largest overcurrent protective device protecting any of the circuits within that raceway or cable. So, if you have several 20 amp circuits in a single conduit, the EGC needs to be sized based on that 20 amp overcurrent protection. This might suggest a smaller EGC size compared to what 250.122b could potentially dictate if voltage drop considerations have led to significantly upsized circuit conductors. Now, how do we reconcile these seemingly conflicting requirements? The key lies in understanding the overarching principle of electrical safety and the intent behind each code section. Firstly, let's consider a scenario where you have #4 conductors in your PVC conduit, upsized due to voltage drop, but all circuits are protected by 20 amp circuit breakers. According to 250.122c, a #12 EGC would seem sufficient, as it corresponds to the 20 amp overcurrent protection. However, the presence of the #4 conductors triggers the stipulations of 250.122b. This section mandates that if the circuit conductors are increased in size for any reason other than ampacity, such as voltage drop, the EGC must be proportionally increased as well. To determine the appropriate EGC size in this case, it's important to look at the circular mil area. If the ungrounded conductors are increased in size, the grounding conductor must be proportionately increased in size according to the increase in circular mil area of the ungrounded conductors. To find the minimum size EGC, you can use NEC table 250.122. For 20 amp circuit, this table typically requires a #12 AWG EGC. However, if the ungrounded conductors are larger than what is required for a 20 amp circuit due to voltage drop considerations, the EGC must be proportionally increased in size based on the increased circular mil area of the ungrounded conductors. The code doesn't explicitly provide a tie-breaking rule, prioritizing one section over the other. This necessitates a practical approach, prioritizing safety and compliance with the intent of both sections. In situations where voltage drop is a significant concern and conductors are substantially upsized, a prudent approach would be to adhere to the more stringent requirement, which would likely be 250.122b. This means calculating the necessary EGC size based on the upsized conductors. For instance, if you're using #4 conductors, which would typically be associated with a larger ampacity circuit, you would need to ensure the EGC is sized accordingly. The information is needed to determine the minimum size EGC. The EGC must be increased proportionally based on the increase in the circular mil area of the ungrounded conductors. Now, the question of when to prioritize 250.122b over 250.122c comes down to engineering judgment and a thorough assessment of the specific installation. If the voltage drop is minimal and the conductors are only slightly upsized, adhering to 250.122c, sizing the EGC based on the overcurrent protection, might be acceptable. However, if the voltage drop is significant, necessitating a substantial increase in conductor size, then complying with 250.122b becomes imperative. To put this into practice, consider the following steps. Firstly, perform a voltage drop calculation to determine the extent of voltage drop in your circuit. This calculation will help you assess whether the conductor size increase is substantial enough to warrant a larger EGC. Secondly, determine the required EGC size based on the upsized conductors, using the circular mil area ratio as outlined in 250.122b. Thirdly, compare this calculated EGC size with the size dictated by 250.122c based on the overcurrent protection. Finally, select the larger of the two EGC sizes to ensure compliance and enhance safety. In summary, while the NEC doesn't explicitly state which section takes precedence, a practical interpretation emphasizes prioritizing safety and adhering to the intent of both 250.122b and 250.122c. When voltage drop necessitates significant conductor upsizing, comply with 250.122b to ensure adequate grounding. When voltage drop is minimal, 250.122c might suffice, but always err on the side of caution and consider the specific characteristics of your installation. Now let's delve deeper into the voltage drop calculation and its impact on EGC sizing. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its impedance. Excessive voltage drop can lead to various problems, including inefficient equipment operation, overheating of conductors, and nuisance tripping of circuit breakers. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use various formulas and online calculators. The formula typically involves factors such as the conductor length, current, conductor resistance, and voltage. Once you've calculated the voltage drop, you can determine whether conductor upsizing is necessary to meet the recommended limits. If the calculated voltage drop exceeds the allowable limits, you'll need to increase the conductor size. This is where 250.122b comes into play. As the conductor size increases, the circular mil area also increases. The EGC must be increased proportionally to maintain its effectiveness. To illustrate, let's consider a hypothetical example. Suppose you have a 20 amp circuit running 200 feet using #12 AWG copper conductors. After performing a voltage drop calculation, you find that the voltage drop exceeds 5%. To mitigate this, you decide to upsize the conductors to #10 AWG. Now, you need to determine the appropriate size for the EGC. Firstly, determine the circular mil area of the original #12 AWG conductor and the upsized #10 AWG conductor. Secondly, calculate the ratio of the circular mil areas. Thirdly, multiply the original EGC size, which would be #12 AWG, by this ratio to determine the required upsized EGC size. In practice, you might need to consult conductor ampacity tables and EGC sizing tables to select the appropriate conductor sizes. Remember, the goal is to ensure that the EGC is adequately sized to provide a low impedance path for fault current, thereby facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. In addition to voltage drop considerations, it's also important to consider other factors that can influence EGC sizing, such as the presence of sensitive electronic equipment. Sensitive equipment may require a more robust grounding system to minimize noise and interference. In such cases, it might be prudent to increase the EGC size beyond what is strictly required by the NEC. Another factor to consider is the potential for future expansion. If you anticipate adding more circuits or increasing the load on existing circuits in the future, it might be wise to install a larger EGC now to avoid having to replace it later. Now, let's discuss some common mistakes to avoid when sizing EGC. One common mistake is to simply assume that the EGC size can always be based on the overcurrent protection, without considering voltage drop or other factors. This can lead to undersized EGC, which can compromise safety. Another mistake is to use outdated or incorrect information when performing voltage drop calculations or consulting ampacity tables. Always refer to the latest edition of the NEC and use reliable data sources. A further mistake is to neglect to properly document your EGC sizing calculations and decisions. This documentation can be invaluable for future reference and for demonstrating compliance with the NEC. In conclusion, sizing EGC and PVC conduit with multiple circuits requires a thorough understanding of the NEC, a careful assessment of voltage drop, and sound engineering judgment. By following the guidelines outlined in this narration and avoiding common mistakes, you can ensure that your electrical installations are safe, compliant, and reliable. Let's expand upon the practical considerations for implementing these code requirements in real-world scenarios. When working with PVC conduit, it's essential to ensure that all connections are properly made and that the conduit is securely supported. This will help prevent damage to the conductors and maintain the integrity of the grounding system. Additionally, it's crucial to use the correct type of fittings and connectors for PVC conduit. Using incompatible fittings can compromise the grounding path and create a safety hazard. When pulling conductors through PVC conduit, be careful not to damage the insulation. Damaged insulation can create a short circuit or ground fault, which can be dangerous. Using a pulling lubricant can help reduce friction and prevent damage to the conductors. Once the conductors are installed, be sure to properly terminate them at the appropriate devices and equipment. Loose or improperly terminated connections can create a fire hazard. When connecting the EGC, ensure that it is securely connected to all metal enclosures and equipment. This will provide a continuous grounding path and help protect against electrical shock. It's also important to label all conductors and equipment clearly. This will make it easier to identify the circuits and components in the future. Proper labeling can save time and prevent confusion during troubleshooting and maintenance. In addition to following the NEC requirements, it's also important to adhere to any local codes or regulations that may apply. Local codes may have additional requirements for EGC sizing or installation. It's always best to check with your local building department or electrical inspector to ensure that you are in compliance with all applicable codes. Finally, remember that electrical work can be dangerous. If you are not comfortable working with electricity, it's best to hire a qualified electrician to perform the work. A qualified electrician has the knowledge and experience to ensure that the work is done safely and correctly. Now, let's address some specific scenarios that may arise when sizing EGC and PVC conduit. Suppose you have a situation where the PVC conduit contains both power conductors and control conductors. In this case, the EGC must be sized based on the largest overcurrent protective device protecting any of the conductors in the conduit, regardless of whether they are power conductors or control conductors. Another scenario is when you have a multi-wire branch circuit in the PVC conduit. A multi-wire branch circuit consists of two or more ungrounded conductors that share a common neutral conductor. In this case, the EGC must be sized based on the largest overcurrent protective device protecting any of the ungrounded conductors in the circuit. If you have a situation where the PVC conduit runs through multiple buildings or structures, the EGC must be continuous throughout the entire run. This means that the EGC must not be spliced or interrupted at any point. If you need to extend the EGC, you must use a listed splicing method that maintains the integrity of the grounding path. Another consideration is the type of grounding electrode system used. The grounding electrode system is the means by which the electrical system is connected to the earth. Common types of grounding electrode systems include ground rods, ground plates, and metal underground water pipes. The type of grounding electrode system used can affect the size of the EGC required. The NEC provides specific requirements for grounding electrode systems in Article 250, Part Roman 3. It's important to ensure that the grounding electrode system is properly installed and maintained to provide an effective ground. Regular inspections and testing of the grounding electrode system can help identify any potential problems. If you find any issues, such as corroded connections or damaged electrodes, they should be repaired or replaced promptly. Maintaining a proper grounding system is essential for electrical safety. A well-maintained grounding system can help protect against electrical shock, reduce the risk of fire, and improve the reliability of electrical equipment. Therefore, it's important to pay close attention to the details of EGC sizing and installation and to follow all applicable codes and regulations. Now let's consider the impact of harmonics on EGC sizing. Harmonics are distortions of the sinusoidal waveform of alternating current, AC, electricity. They are typically caused by nonlinear loads such as electronic devices and variable frequency drives, or VFDs. Harmonics can increase the current flowing in the neutral conductor and the EGC. This can lead to overheating of the conductors and equipment. The NEC addresses the issue of harmonics in Article 220.61, which provides requirements for sizing the neutral conductor in circuits with nonlinear loads. In some cases, it may be necessary to increase the size of the neutral conductor and the EGC to accommodate the increased current due to harmonics. To determine whether harmonic currents are a concern, you can use a harmonic analyzer to measure the harmonic content of the current. If the harmonic content is significant, you should consult with a qualified electrical engineer to determine the appropriate size for the neutral conductor and the EGC. Another factor to consider is the use of surge protective devices, or SPDs. SPD are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power grid disturbances. SPD can divert surge current to the EGC. The EGC must be sized to handle the surge current without overheating. The NEC provides requirements for SPD in Article 285. It's important to select SPD that are properly rated for the voltage and current levels in your electrical system. Additionally, the SPD must be properly installed and grounded to provide effective surge protection. In summary, sizing EGC and PVC conduit with multiple circuits is a complex task that requires a thorough understanding of the NEC, a careful assessment of voltage drop and other factors, and sound engineering judgment. By following the guidelines outlined in this narration and consulting with qualified professionals when necessary, you can ensure that your electrical installations are safe, compliant, and reliable. Now let's discuss the role of the electrical inspector in ensuring compliance with EGC sizing requirements. The electrical inspector is responsible for verifying that electrical installations comply with the NEC and other applicable codes. The inspector will typically review the electrical plans and specifications, inspect the installation during various stages of construction, and conduct a final inspection before the electrical system is energized. During the inspection process, the electrical inspector will pay close attention to the sizing and installation of EGC. The inspector will verify that the EGC are properly sized based on the overcurrent protection and voltage drop considerations. The inspector will also check to ensure that the EGC are properly connected to all metal enclosures and equipment. If the electrical inspector finds any violations of the NEC or the codes, they will issue a notice of violation, or NOV. The NOV will specify the violations that must be corrected before the electrical system can be approved. It's important to address any NOV promptly and to work with the electrical inspector to ensure that the violations are corrected in a timely manner. Failure to correct violations can result in delays in the construction project and can potentially create a safety hazard. In some cases, the electrical inspector may require you to provide documentation to support your EGC sizing calculations. This documentation may include voltage drop calculations, ampacity tables, and equipment specifications. It's a good practice to keep detailed records of your EGC sizing calculations and decisions. This documentation can be helpful for future reference and for demonstrating compliance with the NEC. In addition to the electrical inspector, there may be other regulatory agencies that have jurisdiction over electrical installations. These agencies may have their own requirements for EGC sizing and installation. It's important to be aware of any applicable regulations and to comply with them. In conclusion, the electrical inspector plays a critical role in ensuring compliance with EGC sizing requirements. By working closely with the electrical inspector and addressing any concerns promptly, you can help ensure that your electrical installations are safe, compliant, and reliable.